Well, hi, everybody. Welcome to the module on shelf life, module 6. So I'm looking, and so we have 3 more modules to go, right? We're going to talk about microbiology next week, and then thermal processing on November 20th, which is probably a biggie. That's the one where we discuss all those different abbreviations from retorting, and then packaging, which is a relatively easy one on December 4th. So just plan ahead. And then I have December 11th as the final, but of course you can take it whenever you want. And then we'll be done for the holidays. Yes, so that'll be nice. Just a reminder, I think most of you know that let me do this, that you only need 80% of the points to get the certificate. So I will mail those out sometime before Christmas, but if they don't go out before Christmas, they'll go out right after Christmas. Let's see. Oh, you're welcome to take the quizzes as many times as you like and the final as many times as you like. But please don't memorize the questions because these are my questions. These are questions that I wrote, and I'm sure that the questions on the exam are quite a bit different, maybe even a little more difficult. So don't spend any time memorizing the answers to the questions. Tracy asked some questions in the discussion about water activity from last week. So she specifically asked me about gluten-free bread and why does gluten-free bread stale faster than regular bread? So I found a really nice article, Tracy, from the National Institute of Health, a real official kind of article. But in essence, what it says is that gluten holds water. And we know that, right? So no gluten, no holding water for the gluten, right? And then depending on the starch that you choose, some will be more hydrophilic and hold water more than others, but they're likely to give up their water easier. And so the process of staling is called retrogradation. And so if you search this article for retrogradation, you'll find everything you ever wanted to know and more about gluten-free bread and why it turned stale. So I hope that's helpful. You also asked if there was a complete list of the water activity of different ingredients. I did a brief search. I didn't find anything. But if there was a specific thing you wanted, I would say put that in and then in the search and then put in water activity. Like if there's a specific, because each ingredient is going to be different, right? And then when you combine them and you put them all together in the food, that's going to be different as well. So you can't like add it all up. Right. Does that make sense?
Yep, totally makes sense. Thanks so much.
Oh, good. I'm glad I could answer your questions for you. All right, so today we're going to be talking about shelf life and looking at some of the the learning objective is the negative effects of temperature, oxygen, and light on food quality and shelf life. They also are asking about hurdle technology, which I'll cover next week because there was just too much to cover this week. So then it asks for us to interpret, which I guess means guess, right? Factors such as temperature, oxygen, light, enzymatic, microorganisms, and chemical factors that are going to affect checks shelf life. So I'm going to talk about those a little bit. And prime factors, physical, microbiological, chemical, and environmental. So I think those are kind of the same. I did put in some reading around those if you're interested. So I'm wondering, before I start, if you could put in the chat, I will even open my chat, What are the factors that you struggle with the most when you are looking at shelf life? Is it color, microbiological, like spoiling, like yeast and molds, or is it chemical, rancidity? Okay, so Oleg is saying the green color of vegetables, proper sanitation, off flavors associated with fat, flavor and color degradation. Let's see if I got them all. Perfect. Great. And then John is talking about rotation of product. Obviously, foods don't get better with age most of the time, unless it's a nice stew or a soup, right? So there's always, if the rotation of the product isn't if they're not staying up with it. So Oleg, I'll try and talk a little bit about the color of a vegetable, particularly when we talk about enzymes. And then proper sanitation, what has to do with the microbial load, which we can talk about next week a little bit, the microbial load. But also, if we think about those things and thinking about water activity and pH will affect those things. Oxidation, and then temperature and humidity control. Okay. So those are our, physical factors that have to do with how it's held. And of course, once we ship it out of the plant, we are kind of out of, at the mercy of whoever's buying it. But great. Okay, well, good. Well, let's see if I can answer some of those questions. And when we get to the part, if you have any specific questions around something that I'm going to talk about, because what I'm talking about is really general, I'll try to answer. So the definition of shelf life is the length of time that foods, drinks, and other perishable items have before they're considered unsuitable for sale or consumption. So that doesn't mean rotten necessarily, it just means something that we wouldn't want to eat. And we see there's a loss in sensory quality, nutritional aptitude, spoilage, microbiological yeast and molds, um, and influenced by oxygen and light. So there's four factors, I guess, according to this article that I read, um, that affect shelf life. One is the ingredients in the formulation. And since we were already just talking about gluten-free bread and how changing to going to a gluten-free bread changes the rate at which it stales, that, is one example of ingredients and formulation, processing techniques, how clean the plant is and, how good your temperature control is. And then packaging, can we package it in a way that's going to make it have a longer shelf life? And we'll talk about packaging in that last week, and then storage conditions. So just a little bit about dating. Mostly, I think you know this, and I'd rather talk about some other stuff, but be sure that you know all of these abbreviations. Um, Best if used by is now the recommendation for products, because I don't know about you, but my family seems to think that once that expiration date comes and goes, that food is now unedible. I'm going, really? It just means the ketchup didn't taste quite as good as it used to, or it's a slightly different color. So, best if used by or before. It doesn't imply that it's bad afterwards. It's just better if before. So that's the recommendation. And particularly people are interested in that because of food waste, right? We don't want people throwing away perfectly good food just just because it's past its date. So I think you know what a UPC code is and a SKU. Here's a couple of articles if you have any questions. Any questions about any of that? Oh, okay. Nutritional quality. when we talk about nutrition, we talk about these things, but nutrient losses. So when we talk about nutrition in general culinology, we talked about all the different vitamins and the minerals and, and what affects them in processing. But that's too much information to know. So if we just look at nutrient losses, we have trimming, of course, if you cut off, let's say, the skin, then you lose the fiber, right? And you lose any nutrients that are under the skin. Leaching is probably one of the most important ones to consider, particularly when we come to minerals and water-soluble vitamins. So the vitamins B and C and minerals are all water soluble. So that means that if they spend a lot of time, let's say, already peeled in the cleaning water, then we're going to lose that, right? If the cleaning water isn't acidic, slightly acidic, then it's going to destroy like the vitamin C, which is an acid. So that if the cleaning water is basic, then it's going to destroy the vitamin C or any of the vitamins that are acidic. So leaching, rancidity, enzyme destruction, the browning of a fruit is actually destruction because nobody wants to eat it. And then heat. The more heat we add, the more destruction there's going to be for the vitamins. There are some good things that improve. Aging and ripening actually improve nutrient quality because they break down the fiber. And so some of the things that are trapped in the fiber, then we can digest because we can't digest the fiber. So also phytates are anti-nutrients, we could say, because they bind the nutrients, and so removal of the phytates. So water soluble vitamins, again, what are we concerned about? We're concerned about leaching and loss to oxidation and degradation by heat and light. And I didn't put in here, but I should have pH, right? A basic pH. So I don't know if anybody uses anything like that, but that would all affect it. And the fat soluble vitamins, they're much more stable. And of course, they don't dissolve in water. So therefore, they're mostly destroyed by oxidation or rancidity. The minerals are the most stable, and so we don't worry about them too much. They don't change during processing, but they will leach out. Any questions about any of that? Just kind of a overview. But I think if you can keep these things in mind as you're learning the other ones, then it'll make more sense. So did what I say make sense? Hmm?
Yes.
Okay, good. All right. Uh, be sure you know the difference between fortification and enrichment. Fortification is when you add something that's not already there. So orange juice, calcium fortified orange juice. That's the one that's obvious. There was never any calcium in that orange juice, but it's acid, so makes the calcium more absorbable. And people drink it every morning, so calcium fortified orange juice makes sense. Enrichment is adding back nutrients that are lost during processing. So when we remove the bran, when we remove the bran from the grain, right? Most of the nutrients are in that aleuron layer that's right underneath the bran. So we lose thiamine, niacin, riboflavin, and iron and folic acid. So wheat flour is enriched with those. If we think about processing and a negative, if we add sugar and salt, that can reduce the nutritional quality by putting in, especially for sugar. It's not that sugar is bad, but it doesn't add any vitamins or minerals to it. So sugar is kind of empty calories, we always like to say. So enough of that. Let's talk about something more interesting. So first, let's look at the biological changes that occur. And we talk about biological changes, we're really talking about enzymes. And of course, you remember when I talked about protein, right? I talked about enzymes, and enzymes are proteins. So if enzymes are proteins, what kinds of things will destroy an enzyme? You can write it in the chat. What kinds of things will destroy an enzyme? Heat, acid, great. Okay, anything that's going to denature a protein is going to denature or destroy an enzyme. And remember, and salt, that's right. So remember that the function of the enzyme is based on its shape. And if we destroy the shape, we're not chopping it up into individual amino acids, but if we just destroy the shape, right, and we do that, then the enzyme doesn't work. So, for instance, we were talking about the green color in vegetables, right? And I'm sure that in culinary, you blanched green beans, right? And chilled them really fast, right? You blanched them and chilled them really fast. And then the next day or later on, you could saute them and they stayed bright green. Well, what you did was you used heat to destroy the enzyme that causes the color to change from a bright green to a bleh color, right? So that's generally loss of color in green, particularly has to do with an enzyme. So if we can destroy that, and that's what blanching does, and that's why they stay so nice. Essentially, an enzyme catalyzes, so that's a $2 word that means make the chemical reaction occur faster at a lower temperature. So most chemical reactions require a lot of heat to happen, but inside the body or in our food, we don't have that much heat, so it's going to cause the chemical reaction to occur. So an enzyme comes in and does it. And an enzyme can break things apart or it can put things back together. Just depends. Or it could do a little bit of both. Right. So, but that's how an enzyme works. And notice that the enzyme never changes shape. So why enzymes are so annoying is they're not consumed during the chemical reaction. So if they're not consumed during the chemical reaction, they can keep working and working and working and working until there's no substrate left. So in other words, the whatever you've got it in can get thinner and thin if it's an amylase and it destroys the starch. It could get thinner and thinner and thinner until it's all runny. But an enzyme, as long as it's the conditions are right, it's going to keep working. The other thing is that enzymes keep working in the refrigerator. They keep working, but a lot slower. Even in the freezer, they keep working, but it's a lot slower. So we changes that you see in a product that happen over a long distance of time could possibly be the result of an enzyme, even though it was in the refrigerator. Questions about enzymes? No, freezer burn, Ryan, is a evaporation of water out of the surface of the product. So that's what, because in the freezer, especially our home refrigerators, the freezer, in order to stay frost free, the freezer gets a little bit warmer, and that water becomes more mobile, and then it gets colder again. And so over time, that's what freezer burn is. A lot of you have talked about keeping the names of the enzymes straight. But I really want to emphasize the importance of breaking that long word down. So we know it's probably going to have an ASE at the end. Not all of them, but most of them have ASE at the end. So anytime you see something that says ASE, it means it's going to be an enzyme. So if we look at, when we look at enzymatic browning, right? The enzyme involved in enzymatic browning, because that's in the name, right, is polyphenol oxidase. So this tells me that it's going to be oxygen, and it's going to work on the phenol products. And the phenol is actually the color. It changes the color that makes it brown. So we know there's going to be oxygen and phenol in it, right? Lipooxygenase. And I don't know whether the O belongs to the beginning or the end, but it's going to say lipo means lipid. Oxygenase. This one is also abbreviated lipase or LOX. And this is what causes the rancidity, lipooxygenase, in things with water in them, like butter. Alpha amylase. What do you suppose? Remember the term amylase? What is amylase?
Starch?
That's right. Amylase is a starch. So alpha amylase is going to convert starch into sugar. Going to convert starch into sugar, alpha amylase. And remember that amylase is the straight chain starch. And it's actually present in flour. So we need moisture for the molecules to move around, to get together, to do their thing, to party. So when it's active in flour, it's in flour, and then it becomes more active when you add water to it.
Our
Proteolytic.
starch supplier. Oh, sorry. Our starch supplier, it's kind of crude, but he used to call amylopectin the snotty part.
That's right, right? Yeah. It's kind of the more slimy part, right? Yeah. Um, Proteolytic, proteo must be proteins, right? Proteolytic. So what is it going to work on? It's going to work on proteins. And we know, for instance, that the bromelain, these ones don't have ACE on the end of them, but they are all proteolytic. They belong to the group of enzymes that are proteolytic, and that means they work on proteins. And you know that fresh pineapple can't be put in gelatin because of the proteolytic bromelain in the pineapple, which will break down the gelatin, right, and make it runny. There's also physin and papain that are in Adolph's meat tenderizer that work to tenderize or make mush out of the outside of the meat by breaking down the protein structure. This one, polygalactoroase. I think that N should be in there. Polygalactoroase. So that must have to do with galactose, right? Galactose. And galactose is what?
Monosaccharide from milk?
Uh-huh. Yep, dairy, right? So lactose is glucose and galactose. But galactose is also a fiber. It's part of a pectin fiber. So it's the long chain of galactose rather than glucose molecules. So polygalactoronase is going to break down pectin, and this is actually involved in the ripening of fruit. So when fruit is unripened, it's hard, and when this enzyme goes to work as senescence keeps going, then when the fiber turns to the sugar, galactose, it gets softer. It and hydrolyze is another word for add water, break apart. And then invertase converts glucose to fructose. So try and don't just go, oh, I don't know what that is, right? Try and look at those and try and break them apart and see if you can't find some word in them that you recognize, right? Okay. Does that help with the names a little bit? Thank you, Ben. Thank you.
Hey, Jill, we were working on candies that, the cherry cordials you put the enzyme in there and it breaks down into a liquid over time. So we were doing some tests to do that. You make it as a solid, fill it in the center and let it ripen for a while, and then it'll convert the solid parts into a liquid.
Yeah, that sounds like fun. Did you put a
We just
little THC in there too?
I was gonna say the problem ended up that the THC distillate separated really strong in big pockets, so it would taste really strong. So I feel like we could get somewhere. We just need more. They didn't want to keep paying me to waste time testing things that didn't turn out.
Yeah, that's the chocolate, right? With the liquidy cherry on the inside.
Yeah, yeah, I love those things.
So I talked a little bit about browning before, but polyphenol oxidase. So phenols are in the fruit and we have oxygen, polyphenol oxygen, and they're put together. And then out comes melanin, which is the brown color, and a lot of other stuff. And the polyphenol oxidase remains to do that again. And that's the actual process for the browning of, let's say, a cut apple would be a really good example. And the way we can control it, and we listed most of these at the beginning when I started talking about this, right? pH. So things that can be very sensitive pH because they're proteins, we can denature them if we change the pH. But most of them are most active right around the pH of food. But we could put, if we have our apple, we could put citric acid or vinegar on the apple. Yuck, right? And it wouldn't brown. We can cook the apple. So when we cook the apple, we denature the enzyme. We can refrigerate it. So that's going to be a little bit cooler and it's going to slow it down, but they're still going to brown. We can chelate some of the metal ions because it turns out that copper and iron also are in this activity. We can add sulfites, which of course now is against the law, right? You can't, that's what we used to put on salad bars, right? To keep everything green on the salad bar. But I believe that you can't do that. You just certainly can't do that in California anymore. So there are a few people that are sensitive to sulfites. And then we can add ascorbic acid, which is essentially what ascorbic acid does is it's an antioxidant. So it oxidizes ahead. And this is a fruit fresh, actually. This works really well because the ascorbic acid changes the pH and it also oxidizes ahead and removes some of the oxygen. Questions? So see how when we look at this stuff, it's kind of repetitive, right? So we talk about enzymes and you go, well, whoa, what destroys them? Well, it's repetitive. It works for polyphenol oxidase. It might just work for amylase or one of the other ones, right? So just think about it. This is the list, and it's pretty it's repetitive, always having to do with that shape of the enzyme. Um, Rancidity in lipids. People seem to have a really tough time with this one. So we're just going to start with a review of what the triglyceride looks like. Remember, the triglyceride is a glycerol molecule. There's 3 carbons right here, with attached with additional fatty acids. So when these come together, it's called condensation. And when it goes apart, when a water molecule is added back in there, it's called hydrolysis, or breaking it apart. The attributes of the fat are dependent on the fatty acids that are present. If there's a lot of long chain fatty acids without any double bonds, it's going to be solid at room temperature because they're all going to pack nice and close together. The more double bonds there are, the more bends there are going to be in the fatty acid. So the more bends, the more liquid it's going to be at room temperature. And we talked a little bit about cis and trans. That has to do with the side of the hydrogen. But essentially, trans, it makes the fat a straight line, so that it acts like a saturated fat. Cis, both of the hydrogens are on the same side, and so there's a bend in the molecule. So there's 2 kinds of rancidity. The first is hydrolytic rancidity. And if I look at that word hydrolytic, what does that imply?
Water.
Water. That's right. Hydrolytic. That means water. Okay, so hydrolytic rancidity must mean there's going to be water in there somewhere. And in fact, remember I told you that hydrolysis is where these break apart and a molecule of water is added in. So hydrolytic rancidity is going to be a breaking off of the whole fatty acid. If it's a short chain fatty acid, it means it's a small molecule, it's going to evaporate into the air and it's going to smell bad. And so butyric acid in butter is a very short chain fatty acid. And so it's volatile. So when butter goes rancid, what you're smelling is a short chain fatty acid that's broken off by hydrolytic rancidity.
I think I told you before, Jill, I have a little sample of pure butyric acid. It
Ugh.
smells absolutely atrocious.
I'll bet. So in this chemical reaction cannot occur at the normal temperature of food without the help of an enzyme. And the name of that enzyme is lipase. So lipase is it's the enzyme that's going to break off one of the fatty acids, or in this example, all 3, but generally only 1 or 2, not the whole bit. So is that clear? So that's hydrolytic rancidity. Needs water, right? And an enzyme, because this chemical reaction will not occur without water and an enzyme. Questions about this? But while it makes butter tastes yucky, it makes for great cheese. Right? Really nice cheese. Stinky cheese, my favorite kind. So how we test for this is to test for free fatty acids. So are there free fatty acids? Then we would know that some of these guys had broken off. That's how we test for free fatty acids. Questions about hydrolytic rancidity. It's the least common. Most of the time, we'll talk about the other kind of rancidity in a little bit. Most of the kind is oxidative rancidity. So that was the biological one. So biological means enzymes. Chemical reactions. So these don't require an enzyme, but generally they require some elevated heat for them to happen, right? So Maillard reaction is a chemical reaction between a protein and reducing sugar and with the presence of heat. And all sugars are reducing sugars except for sucrose, table sugar. And that's really what you need to know about that. Produces the browned color and the flavor, right? Yummy, yummy, yummy. The reaction is favored by heat and time. pH, notice a nice neutral pH. Moisture is required, an intermediate moisture, not too much moisture, not too dry, in the middle. And moist heat cooking doesn't brown. We know that when you have like a stew or something like that. So to control browning, we can reduce the temperature because it's a chemical reaction, so it's going to go slower. We can lower the pH. We can adjust the moisture to very high or very low levels, and we can remove the sugar. An example of that is they take the lactose out of dry milk in order to prevent it from browning. In California, acrylamide is considered cancer causing, and so they're trying to figure out how to get rid of it. I don't know, good luck. So that's why they're picking on frying. Questions about the Maillard reaction?
Remember we were talking about in when you get old cans of condensed milk, how it browns, how the color changes? So I talked to my chemistry nerd friend, and he's pretty convinced that that's a slow Maillard reaction over time.
I think so. Yeah. I don't know. One of the things I used to do when I was teaching my foods class was I'd take a can of condensed milk, right? Sweetened condensed milk, and put it in some boiling water and let it boil for a half an hour. Oh my God, it makes the most wonderful tasting caramel sauce ever.
So delicious.
It's
Oh,
called dulce de leche in basically every Latin or Hispanic origin country. So
yeah.
dulce de leche is the caramelized sweetened milk.
Oh, it's the best.
Yeah.
The best. I could eat it straight out of the can. Best.
Yeah. Yeah, yeah. If you send it for like 2 hours, it'll get really rich. It'll really get fudgy on you. So it's yeah, that's
Yeah.
a special
Just in
thing.
boiling water.
Yeah, just in boiling water.
Yeah. You just take the can and don't open it. And you just put it in boiling water and you just keep heating it on a low simmer. Don't let the water boil away. And do you have to cover it, Daniel? I don't remember even covering it with water.
You can, just to mitigate like the evaporation loss and having to refill it and lowering the temperature.
Mhm.
I would definitely keep it covered, and put ample water and get a pot that can get rolling.
Yeah.
And yeah, and just send it away, But it is pretty fascinating how delicious that is. The first time I realized that's how my grandma was making that, and it wasn't like some laborious process, I was like, nice one. Yeah, yeah.
Yeah. So, yeah, you want to boil it for like an hour. It's a long time.
Yeah.
The longer you boil it, the stronger the flavor. Right.
Right.
Yeah. Yes, and I would agree with you, Monto. It's a Maillard reaction between the protein and the sugar. But also the baking of bread, that's a Maillard reaction. The brown color, the grilling of meat, those are all Maillards. All right, so now so earlier I talked about hydrolytic rancidity. So this is the most common type of rancidity, and it's oxidative rancidity or auto-oxidation, it's also called. And what happens with oxidative rancidity is that oxygen gets in here. And remember, these double bonds are weaker than the single bonds. So oxygen gets in there and breaks these double bonds apart. And what do we end up with? This little fragment right here, which is stinky, smells rancid, right? This little bit right there is stinky. So it smells kind of rancid. So that's what oxidative rancidity is. It is the most common kind. It's what happens to potato chips and crackers and anything that's dry. So it has to be a dry so that the oxygen can get to the fat. And the more polyunsaturated the fat is, the more likely you're going to have oxidative rancidity, right? The more double bonds there's going to be. It's called auto-oxidation because once it starts, it keeps going and going and going and going and going, right? So we get the initiation, the propagation, and it just goes around and around and around. The more radicals, the little oxygen radicals are produced, the more it goes around. It goes around until there are no more double bonds. Right? And then it terminates, because essentially it has run out of double bonds. So when they ask you, there's 3 stages: initiation, propagation, and termination. Those are the 3 stages of oxidative rancidity. So how do we control that? Well, if it's colder, the chemical reaction doesn't occur. That doesn't help much with potato chips. Um, Low water activity, it's going to be more. So if you raise the amount of water that's in there, again, not going to work for potato chips. Reduce the exposure to oxygen. So use some kind of a nitrogen flush or something, some way of removing the oxygen from the package. That will help, because listen until you open it, that is, right? And the type of fat, you could use a more saturated fat, which is probably frowned upon. You can add an antioxidant. So the most common one that's added to vegetable oils is vitamin E. The chemical name is tocopherol, vitamin E. So if you look on your corn oil, it'll say that it has tocopherols added to it. And essentially what happens is it oxidizes before the fat does. That's why it's called an antioxidant. The more unsaturated it is, the more trouble. It requires or is accelerated by some metals: copper, iron, manganese, and chromium, trace minerals in your food. So if you put in a chelating agent, something that's going to bind up these copper, iron, and manganese, then the rate is slower. And keep it out of light. So packages that have rancidity are, in a little aluminum package, that's shiny on the outside to keep the light out. Opaque. There are some natural antioxidants out there: rosemary, and ascorbic acid, tocopherols. And then there's a whole bunch of synthetic ones. Questions about it? So the difference between, if I say oxidative rancidity, we're going to think oxygen and double bonds, right? And if I say hydrolytic rancidity, we're going to think water, water, right? And short chain fatty acids and an enzyme. All right. Does that make it clear what the difference is? Because when I look at the final exam, the most missed questions have to do with the difference between oxidative and hydrolytic rancidity. So I'm making a big deal out of it. Okay. Any questions?
So it's oxidative is oxygen double bond and the attacks a double bond. Hydrolytic is water and short chain fatty acids
And a
and
enzyme.
an enzyme.
Yeah.
Okay.
All right. We can test. So when you when you get your fat, it comes with an analysis. And one of the things that is always included is the peroxide value. And the peroxide is the little fragments that broke off. So the peroxides are this little bits right here. So that have broken off. So that's the peroxide. So they can test that. All fatty acids are going to have some peroxides, you know. But the fresher it is, the lower the number is going to be. We can also do an oxidative stability test. And the resistance of the fats or oils to oxidation, that's less common. We can do sensory test. We can do the melting point, but remember, melting point is a misnomer. It's the melting range. So, because each fatty acid is going to be liquid or solid based on its own individual properties or number of double bonds. It's like if you think about the olive oil you put in the refrigerator and gets all crystally. So the more saturated fatty acids are making those crystals, while the more polyunsaturated parts are still watery. So it's really a melting range. We can also test for solid fat. And we can also do an iodine value, which will give your the iodine number, degree of unsaturation, because the more iodine, the more unsaturated it's going to be. So there's a lot of different kinds of tests. Color. So they can do that and they can measure the color. Okay, if you have a lot of money, you could do a that word. Chromatography. So yeah, so the Lovobond measures the red and yellow colors of the fat. So the higher the red value, the darker the oil. Any questions? I covered a lot, but I think a lot of this is a review. But did I cover something too fast? So I know that this particular section has a lot of reading in it. Hopefully some of that is just review from your experiences when it talks about different kinds of foods and from your culinary experience. So I just picked the sciencey parts to talk about. Anybody have any questions?
All good. Thanks, Jill.
Oh, I like that. Okay. Let me